Hi, this is Joe from the Math Perimeter, where I help make undergraduate mathematics accessible, engaging, and approachable through various forms of content. Today I will be talking about basic differentiation rules, including the power rule, the constant multiple rule, and the sum rule. For more information about this topic, please refer to the article in the description. Today I will be talking about how to differentiate the following functions: f of x equals x squared plus 7x plus 12, g of x equals x plus 1 squared all over x, and h of x equals x plus 2 all over the square root of x. To differentiate these functions, I will use the rules previously mentioned, as well as algebraic manipulation. We begin by differentiating the function x squared plus 7x plus 12. To differentiate this function, we notice that it is the sum of three simpler functions, so we use the sum rule to obtain f prime of x equals x squared prime plus 7x prime plus 12 prime. We are now ready to differentiate the first and third functions, and we'll be ready to differentiate the second function after we use the constant multiple rule to rewrite this as f prime of x equals x squared prime plus 7x prime plus 12 prime. To differentiate the first function, we simply just use the power rule to obtain 2x. For the second function, we differentiate it using the power rule, noting that the x has an implied exponent of 1. Carrying out the power rule, we obtain 1, and multiplying that by 7 gives 7, and the derivative of the constant is 0, so the derivative of 12 is 0. Putting all this together, we obtain our final answer of f prime of x equals 2x plus 7. We now differentiate the function g of x equals x plus 1 squared all over x. Unlike the previous example, before applying the differentiation rules, we must first rewrite the function using algebraic manipulation. We start by rewriting the denominator using negative exponents, which gives us g of x equals x plus 1 squared x to the negative 1. We now rewrite x plus 1 squared as x plus 1 times x plus 1, giving us g of x equals x plus 1 times x plus 1 times x to the negative 1. We now multiply the first two factors using the double distributive property, which gives us g of x equals x squared plus x plus x plus 1 times x to the negative 1. This can be simplified by combining like terms to give us g of x equals x squared plus 2x plus 1 times x to the negative 1. Distributing the x to the negative 1 term and using exponent rules, we arrive at the function g of x equals x plus 2 plus x to the negative 1. We can now differentiate this function. To begin, we notice that the function is the sum of three simpler functions, so we apply the sum rule to obtain g prime of x equals x prime plus 2 prime plus x to the negative 1 prime. And like the previous example, we do not need to use the constant multiple rule, as these functions can already be differentiated. The first function was differentiated in the first example, and its derivative is 1. The second function is a constant, and as we previously discussed, the derivative of a constant is 0. Lastly, the third function can be differentiated using the power rule, giving us negative x to the negative 2. Putting all of this together, our derivative is g prime of x equals 1 minus x to the negative 2. This is a valid answer, but it's nice to have the function in the form of our original function. To get it into the similar form to our original function, we begin by rewriting the negative exponent as a positive exponent, giving us g prime of x equals 1 minus 1 over x squared. To subtract these fractions, we need a common denominator, so multiplying the first term by x squared over x squared, we get g prime of x equals x squared over x squared minus 1 over x squared. Subtracting the fractions, we get a final simplified answer of g prime of x equals x squared minus 1 over x squared. Lastly, we want to differentiate the function h of x equals x plus 2 all over the square root of x. Like the previous example, we must use algebraic manipulation before we can differentiate this function. We begin by rewriting the root as a fractional exponent to obtain h of x equals x plus 2 all over x to the 1/2. We now want to rewrite the denominator using negative exponents, which gives us h of x equals x plus 2 times x to the minus 1/2. Distributing the x to the minus 1/2 term gives us h of x equals x to the 1/2 plus 2x to the minus 1/2. We are now ready to differentiate this function. To begin, we notice that our function is the sum of two simpler functions, so we use the sum rule to obtain h of x equals x to the 1/2 prime plus 2x to the minus 1/2 prime. We are now ready to differentiate these functions using the power rule. The derivative of the first function is 1/2 x to the minus 1/2, and the derivative of the second function is minus x to the minus 3/2. Summing these results, we get that h prime of x equals 1/2 x to the minus 1/2 minus x to the minus 3/2. As with the previous example, this is a valid solution for our derivative, but it's nice to have the form of our derivative match the form of the original function. To get the derivative to be in this form, we begin by rewriting the negative exponents as positive exponents, which gives us h prime of x equals 1/2x to the 1/2 minus 1/x to the 3/2. To combine these fractions, we first need a common denominator. To get this, we multiply the first fraction by x over x and the second fraction by 2/2, giving us h prime of x equals x over 2x to the 3/2 minus 2/2x to the 3/2. Combining these fractions gives us h prime of x equals x minus 2/2x to the 3/2. Rewriting the fractional exponent as a root gives us our final answer of h prime of x equals x minus 2 all over 2 root x cubed. Thank you for watching. I hope you enjoyed the video. Please like and subscribe. Thank you. See you next time.